Hello, I'm Jomora from the University of Edinburgh, and I would like to tell you about our recent work on planning an MPC for non-prehensile planar manipulation tasks with complementarity constraints. Let's consider this top view illustration of a task where the goal is to push the red object, the slider, towards the green target using the dark blue contact dot, the pusher. We can plan a motion of the pusher that achieves this task and execute it with a robot. The video on the right shows a physical simulation of just that. However, as you can see, the real object in red significantly deviates from the planned trajectory in gray. Note as well that in this example, the sliding motion between the robot and the box occurs in spite of the planning enforcing a sticking contact between them. This happens due to the non-prehensile nature of the task. In the absence of a full grasp of the object, any mismatch between the prediction model used for planning and the physical environment will lead to deviations of the desired motion. Therefore, in addition to a planning method, we need to find a controller to keep track of the nominal trajectory. Due to the non-holonomic nature of the system, such controller also needs to have a predictive horizon. Therefore, we need to find a motion model for the pusher-slider system. We use the same model as in Zeus and Hogan's works. The resulting system state contains the position and orientation of the slider and the relative angle of the pusher. The control consists of the normal and tangential forces applied by the pusher to the slider, as well as the relative displacement. We also need to consider additional contact constraints. For instance, the pusher can only apply positive normal forces. Other constraints depend on the contact mode. For example, the contact force will be within the friction cone if the contact is sticking, and on its boundaries if the contact is sliding. One way of encoding these contact modes on a trajectory optimization problem is through a mixed integer approach. In this approach, in addition to the constraints of the motion dynamics and the state control boundaries, we add a set of binary variables to the optimization that define which mode is active at each given instance in time. By linearizing the motion model around a given path, then this problem becomes the mixed integer quadratic program proposed by Hogan and Rodriguez. In this work, we propose an alternative way of writing the constraints of each contact mode in the form of a complementarity constraint. These allow us to rewrite the trajectory optimization as an MPCC, removing the need for integer variables, which tend to make optimization problems scale badly due to their combinatorial nature. We compared the MPCC approach for tracking a nominal trajectory with the mixed integer QP and realized that the MPCC method is better at handling large disturbances, both in terms of the tracking error and computation time. For planning, in comparison to the mixed integer nonlinear program, the MPCC computation time scales better with the increase in the time horizon. It is also able to handle simple obstacles, unlike the mixed integer approach. We deployed our method in a physical setup using the KUKA LWR robot to push an object tracking an ellipsoidal trajectory. We tested its ability to recover from both modeling errors and additional large disturbances. Finally, we showed that we can use the same MPCC formulation both to plan a path with sliding motion while avoiding an obstacle and to track it. Thank you for listening.